Okay, last time in applied dynamics 2, applied mechanics 2. Oh, I guess we still have 2 minutes, but this is a recap. We were looking at 2 different reference frames. One was fixed, another one's moving at a constant speed, thinking about what are the forces applied to this thing, how do we define its position, its velocity, and today we're trying to tie all that together. So we decide. And for the most part, like once you choose a reference frame, your position and velocity are those are fixed numbers. Like it has an XY position, or it has an R, like a radius along a given unit vector. So we weren't doing anything like, I don't know, not like a lot of math or anything. And today we're trying to wrap it all up. We figured out what the moment was last time, because we drew the free body diagram. We figured out around O prime, so the moving reference frame, there's 0 moment. There's no torque applied around that point. What is the moment around O, around the fixed point? Is it also 0? Maybe. We can use same definition, right? The position RPO, so the absolute position of our point, crossed with the sum of the forces around O. And we want to know, is this 0? Is it still 0? In a statics problem, if some of the moments around one point is 0, everywhere it's 0, right? But in dynamics, can we still say the same thing? That if it's 0 one place, is it still 0 somewhere else? That's what I want to know right now. And kind of backing up a little bit, let's grab our definitions that we need. So we went through the work to say, this is my RPO, and we had already said, like, this is my FS. So can we say that that moment is still 0?
No, because I would probably fail. I said, he got an internship like a month ago. And I think he was a protest. I said, what's he doing? For scheduling. And he goes, yeah, I was like, I don't know. That's why he's like looking at me, he's like, oh, like it's 7 days. I think that's for something that really like wants if he goes out, high will hit something. Because when he goes out and gets like I was like in my hair, so I was like, yeah, I mean, it's still worse. They're moving back. Right? Or not moving from the point, but I mean, one more still only if the spring was attached. Oh, it's attached. I understand it's more to that's a good thermal makes sense. It's just like it's okay, because you're doing like your phone doesn't have kids still. Well, if the cross product 0 means like the two vectors are we say the same direction. Well, I guess what is the direction? If you're looking at it, so I guess but now where we were looking at R they're both right. Now we're looking at here.
So what do we think? Still 0 or not 0 so far for the moment from around O rather than O prime. So we have a spring being pulled to O prime, and we're looking at moment around O. Yeah?
Wouldn't it not be zero because there's a component that isn't ER?
Yeah, so here I've got these two parts to this now, right? So when I say V0T B1 plus RER crossed negative K R minus, oh, why did I do it negative? I still have that R cross ER, so that one's still going to be 0. But the sum of the moments around O is now going to be like a negative K V0T R minus L0 B1 crossed with that ER. And remember last time, well, maybe you don't remember. I'm not telling you like you must remember this. I'm saying like there was a time when I said this, and if you remember it, great. If not, then let's read. I was using these mixed coordinates, like a B1 and an ER. So I know that I can convert from one to the other. I can go back and forth however I want. At this point, when I'm doing a cross product, that's where it makes sense to like get them all into one system rather than, because it made sense to kind of leave them like this so that I could cancel this out rather than doing a whole bunch of sines and cosines and trig identities. It's like, it sounds like a lot of work. Okay, so ER is cosine theta in that B1 plus sine theta in that B2. Again, that's always why I say the x-axis is theta equals 0, so I never have to like rederive what is that ER vector. That's just how it works every time. And then my E theta would always be that negative sine and cosine. And again, not something I expect you to like just pull out of the air. It's just that I've done it so many times. And one day, 10 years from now, you'll have done it so many times that you'll be like, I remember this. The B1 cross B1 cosine term goes to 0 because B1 cross B1 is 0. B1 cross B2, what's that? B1, so X crossed with Y. What? It is 1, magnitude 1, but what direction? Because cross product is weird. It still gives you a direction. It changes. In the Z direction? Yeah. Yeah, we can call it either B3 or Z or EZ. EZ. Easy sounds good. But there's nothing easy about this. We'll call it B3. All right, so what's going on here? Why do we have two different moments? One is always 0 for all time. The other one is 0 at time 0. And that makes sense because that's when they're both in the same spot. And then as time increases, it just gets bigger and bigger and bigger. So at time infinity, I have infinite moment. Why is this happening? What is wrong with the world? It's those damn tariffs. That's the problem.
Maybe since you're looking at it from the O coordinates, maybe it's just because it's getting further and further away.
Yeah, like it keeps growing. Like we keep increasing that moment arm because of how this system is set up. And here, do you know why that would, like what kind of system that would look like? Where this is actually the thing that you care about? Any ideas on that? Maybe not, because it's like a little abstract. You ever seen those like at shipyards and stuff? It's like a traveling kind of cable car sort of thing that can raise up and down. Pendulum is, for small angles, it is a spring mass kind of system. So if it starts moving around in a circle, it's never going to stop. It's just always going to be moving in that circle like that. So in this case, if we think of this as like my O prime coordinate system, there's never a torque created on that support system, at least based on how this thing is swinging around. But on the support structure, there's absolutely, as something is moving and it's moving away from us, there's absolutely a torque needed to maintain, like, otherwise the system, like, as you keep moving it away, it'll start swinging back and forth, right? So if you want your cable car to go where you want it to, then you need some kind of torque to keep it still, like some kind of fixed torque like that. So nice lesson. Just because moment is 0 in one location doesn't mean it's 0 everywhere else, unless it's a static system. If things are not moving, then that would be true. Or if it's quasi-static, that's the other case that we looked at. So the changes in angular momentum are roughly 0 in any case. All right, cool. Oh, and it just gave away. What is the sum of the moments equal to? If you apply twisting force, a torque, what happens to things? Sum of the forces is a change in momentum, right? So if I apply a force, something will increase speed and move forward. Or if I twist something, what happens to it? It'll twist. It spins, yeah. So it's spinning motion, right? Yeah. These aren't like, I'm not asking like, well, if you factor in the average speed velocity of an African swallow, then no, it's like, if you twist something, it's going to start spinning. It's not going to move. If you twist it, it's not going to go that way. It'll start spinning, so it'll increase angular momentum. It's the main thing. So if I have 0 twisting, there's no twisting torque on the system, what does that do to my angular momentum? There is none? Close. There's no change. If something's spinning and I apply no torque to it, it will just keep spinning, and it's never going to stop spinning.
You said that is angular momentum, right?
That is angular momentum. So the sum of the moments, when we said the sum of the moments is 0, that's equal to the change in angular momentum around O prime. So the total angular momentum is always constant. So we're looking at like conservation angular momentum. Space is a great example of that because gravity can't apply a torque. So angular momentum is always constant for like if you're only considering gravity around a certain point. But it's not always zero, right? Because depending on your reference frame, you can always create torque. Oh, and then we're supposed to do this part, right? Now we're trying to find angular momentum around P0, O prime. What is angular momentum for an object? Do we know what that one is?
Rotational momentum.
Yeah, rotational momentum. How do we get that? What's like the formula for rotational momentum? Because it's describing like how much momentum it has in terms of like spinning momentum.
Or is it just for itself like rotating?
So if we only considered around itself, that would be like,
So this is a dot, like thing drawing the fingers and then
yeah, exactly. So for a point mass, the angular momentum around itself, like around its center of mass, is zero because we already assumed that it has no radius, like it has all the masses in one spot, just plugged in right there. But we want to know what is angular momentum around O prime. So like it's moving around O prime. All right, we'll do a quick, this is like the cliff notes of derivation of angular momentum. Yeah, let's put it on a new page. Sum of the moments is MA, right? Or sum of the moments is change in angular momentum. If I take R cross F, I just define sum of the moments. Because the resultant, if I take total resultant R cross with resultant F, I just have the resultant sum of the moments. And then on the right side, I have the change in R cross and that is my angular momentum, R cross MV. And again, this one's like very, very short, very quick, short and sweet. What is angular momentum in terms of like what formula do we use for it? So here I'm saying R, P, O prime crossed with M, V of P, O prime. And I'll write out those, really we just chose like polar coordinates, so our definition is based on polar coordinates, but let's write them out again. And now we're just taking the definitions that we have, plugging them into that HO prime value, and calculate what is angular momentum here. All right, good step. Everywhere? All right. Like the fact that we have two. For that one, it's always the same definition, like position cross with momentum is equal to momentum. If we have like rigid bodies, then we can use moment of inertia. And then I guess we could use moment of inertia here if we wanted to. For a point mass, I is m/r squared. Yeah, it's just like a definition. Angular momentum is always something that has to do with like position and momentum. How much these are? How much is that relative mass? P spinning around over yeah, understand where. Yeah, this one, like, we're kind of doing like a tour of angular momentum and moments with this problem. So it's like a general what are results. Numbers. I don't know if that would make it easier or more confusing. Yeah. Yeah.
So much they try to grab that.
Okay. Oh, like if we look at any momentum around the point P itself. That
Point
one's
is
like
like point piece.
point P is yeah is the mass.
Yeah.
So
Oh,
yeah,
okay, so
that case,
yeah, makes sense. That's
yeah. Yeah, you just do one at a time, like ER cross ER, this down to 0, and then ER cross E theta. And there it's the same as if you had like X crossed with Y. And because that's the same thing as if you had like an X and a Y, because they're both 90 degrees to each other. So we end up with a unit 90 degrees to both of them. We could call it like E3 or EZ, anything to say like it's coming out of the page. Okay. Better than half the last. Oh, nice. Yeah, like a theta dot. Oh, yeah. Cool. That makes sense. So some of this stuff like does get confusing, but if you always step back to like just what is the definition, how do I, and that's why we went through the process of like saying this is position, this is velocity. Now in a new frame, what is position, what is velocity? Because now we can kind of take just exactly momentum is a position crossed with mass times velocity. Plug in those values, and now we have like an equation that describes angular momentum. And then we can kind of back up and try to figure out, like, does it make sense? Is that what we're looking for? So I have R ER crossed with R dot ER. Oh, whoops, I forgot my mass. Mass R dot ER. So mass is a scalar value. It doesn't really change anything. And R dot, R theta dot, those are also just scalar values. They're just describing like how much is radius and how much is angle changing. And then the unit vectors, that's really where we're doing the cross product work. What's ER crossed with ER? 0. So those first, that R times R dot, that whole term goes to 0. What about ER crossed with E theta? What do we come up with there? Yeah, like B3, so it's coming up out of the page. So I have M R squared theta dot in that B3 direction. And this is true anytime you say, like, all right, I have a polar coordinate system, this is always your angular momentum, like a point mass traveling around that reference frame. And if you look up, like, what is moment of inertia for a point mass, it's mr squared. So we just derive, like, that I is mr squared for a point mass. Kind of nice when things work out the way they should. All right, so let's come back up here. I don't know why. The last step in here is trying to figure out, like, why is angular momentum conserved in one frame, but it's not conserved in the other. But we already figured that out, right? The moment in one frame, in O prime, is 0. Moment in O is not 0. Like, it keeps changing over time. Sometimes it's 0. Like, if theta is 0 or 180, then yeah, now we have no torque because the spring is in line with our, like, support structure. But most of the time, when theta is not those, like 90 degrees, now we have largest torque. So some moments around that O prime. And what did we get for that one? Negative kV. So just trying to write out like, look, our moment is a function of time, so there's going to be some change in that angular momentum there. And we're done. What do we think? Hard steps, easy steps? What were the hard parts and easy parts?
Understanding how what to pull out of the cross product.
Like what, that was easy or hard? Oh, hard, of like, what is the cross product? Yeah, cross products in general get kind of weird because now you're looking at, yeah, nothing stays like linear. Cross products always create like, you can't just add terms up together with cross products. They get a little wacky. Sometimes they're 0, sometimes they're not, sometimes they're 1. This is the way that I prefer to do cross products, where I'm just looking at like the unit vectors themselves and crossing them, rather than, I think the way that I've seen it most of the time is like you put the ER, E theta, V3, so then we would have an R, a 0, 0. Have you seen this one before? Is that how you used to do cross products? So like, so then like the ER is 0 times ER, kind of going this way, right? Plus 0 times E theta, and then plus R squared theta dot V3, and then minus a 0 B3 minus and minus like another that's how I've seen people doing cross products, but I just find it's like extra work to like write it all out in that form. But it's the same, you'll get the same result. It's like plugging those in that way, because we still end up with like m r squared theta dot, like that. Just seeing it in another form. But main thing here is just kind of remembering like moment is always just position crossed with forces. The angular momentum is position crossed with that linear, mv. And if you're always defining them that way, then it'll work out, at least for kind of point mass stuff. Yeah.
In part C, where you're doing the sum of the moments for O, you pulled out the negative K VOT. Is that because those are constants?
Sorry, like down here?
Yeah. For like the sum of the moments for point O.
Yeah.
Like that negative K V naught T came out. And is it because those are constant values?
Yeah, so everything that's not an actual, at least when we write out vectors in the form of like something times a unit vector, whatever that something is just, it's a scalar value, in the same way that like mass doesn't have a direction. The spring stiffness has no direction. It's just big or small. And then R is the radius. Again, it's just either big or small. But then it's unit vector ER. That's telling you which direction it's facing. So that's how I can like get all the unit vectors in one spot and do the cross products, and leave all the extra all the other stuff that's like big and small scalar terms, collect all those together.
So like since we're working in polar, all the R and theta variables stay inside the cross product?
No, R and theta those are all just scalar values. They're just describing like how big is, yeah. So R is telling you how big is the radius, like how far away am I? So very much like a scalar distance. And then theta is again like just how big of an angle am I? And theta is like one of the values that it doesn't really matter if it goes to infinity, because you always end up back where you started. So you can make theta as big as you want. Yeah, so that's how I ended up with, like, when I was trying to do this cross product, it just brought everything that wasn't a unit vector outside and just looked at B1 crossed with B2.
Oh, okay, so that R minus L naught is getting pulled out too.
Yeah,
Okay.
yeah. Yeah, so all this, if we look at it, is like, and then let's do another. And then we'll do pink for our cross products. Yeah, thanks. That was a lot, but we're good. We made it. And we're stronger for it. Let's copy this guy. Okay, next problem that we're looking at is a marble. It rolls down a ramp, hits the table. Now it starts rolling across the table, and then it falls off the table. We want to know, like, after it falls off this table, it's going to go some distance and land here. How far is it gonna go as it leaves the table? What's your first thoughts here? What are some things that will work or not work, or maybe there's questions about? Like what's your engineering process? Yeah. Sorry?
So it starts with that much potential energy at the height.
Okay.
Times H1 plus H2, and then ends with the same amount or something.
Yeah.
Eventually it's gonna stop moving, right? But all that distance is gonna force times distance equal to that energy.
Okay, so thinking about let's think about conservation of energy, what's work done on the system. Nice. So if we're thinking about stages where energy is conserved, is it conserved throughout the whole process, until it hits the ground? So if we start with What do we have? 0.05, so I don't know. Let's say we have 0.5 joules per meter, and I don't know. Let's say we have a quarter joule. Do we end this process with that same quarter of a joule? Is it all going to be conserved the whole way through? No? Why not?
Friction.
Maybe friction?
Some of the energy gets translated into the rotational energy.
Okay, so we'll have some rotational energy, but rotational we can still, I mean, it's still like kinetic, right? Like rotational energy is kinetic energy. Yeah.
I'm sort of thinking about, because on the ramp, the diameter is being like forward movement.
Okay.
But I think once it falls off the edge, it's just accelerating downwards. So I don't know if that would factor into like the distance it rolls. But
Okay.
I'm not sure.
Yeah. Yeah, the distance that it like goes through the air.
Yeah.
Yeah. All right.
Yeah, I think we just need to find like the velocity before it falls off the block, because the distance it goes isn't affected by gravity, it's just how fast it's going.
It's not affected by gravity?
Well,
oh, say.
They're in two different like reference frames.
Okay.
So I mean, the gravity, I don't know how to describe it. Like if you just dropped it from that point, it would hit at the same time as if it were rolling off that point.
Yeah, like the time, how long
Yeah.
it's in the air is only dependent on gravity.
Yeah.
And the distance that it travels is.
So as long as we know the velocity,
Yeah.
we'll know how far it will shoot.
Okay. Yep. Is energy conserved when we go from the ramp to the table? So if I have MGH1 and it all gets turned into kinetic energy, do I lose any kinetic energy as it comes off the ramp?
I don't know, maybe at the edge of the ramp, like whenever the ball hits the table, it the impact with like that energy may be lost from vibrations as it impacts onto the table.
So an impact.
So I believe it's minimal.
You think minimal though? So impact and impulse, those are like same thing, right? So there's definitely an impulse being created on this marble. So here's a question: do speed bumps slow you down? Somebody pointed out there's also a psychological slowing down because you hit the brakes before you go over the speed bump. But let's say you don't hit the brakes, you're not adding gas. Does the speed bump slow you down? Yes?
Yes, it does.
How does it slow you down?
Well, bump is like a hill, right? So
Okay.
you should like technically maintain all of your kinetic energy. It'll just like change it to more words because you're going up there.
Okay. So we're going up. So yeah, we're right. If we're in here, I'm gonna do a little. And let's just think about it as like we're just on like a unicycle, right? So initially, I'm moving forward at MV0. What happens when I hit that speed bump? Am I still moving at the same speed as I go up? Yeah.
I forget the specifics, but there's like the thing in physics with collisions, and I'm thinking if it's like a collision between the speed bump and the wheel, it would be sort of like inelastic. since it's not like bouncing off.
Yep.
So I guess there'd probably be a loss, or, you know, from the impact would be transferred into some other form of energy. So I don't know if it would all be conserved, but
Yeah. So if you hit a speed bump and it was a perfectly elastic collision, then I mean you do a wheelie as you can't, because whatever direction you hit the speed bump at, it would just send your car up by that big of a force. So we've got something that's just like creating an impulse and not letting anything move through that surface. And like it's kind of hard. So we got that, and then so something happens there. Let's look at just this part. I'm gonna call it like MV leaving. As I'm like so I hit I have to change my momentum, go up and over the speed bump, and as I'm coming down off of it, whatever my leaving velocity is, there's only one component that's parallel to the road. The other component is going down into the road. So whatever's going down is that's gone. I don't have that speed anymore because it's just gonna, and if I do have it, then it's just bouncing. It's just me bouncing down the road after that point. So as I leave that speed bump, the only thing left is like that MVX, because I had a big impulse pointing upwards. Are we out of time? Oh, we're out of time. All right, sorry about that. But speed bumps work. They apply big impulses by not letting your car go through concrete. Same thing will happen here. On Friday, we have Mr. Mundiwala coming back for another guest lecture. So give him, think about like how he's approaching it, and then he'll be able to practice being up in front doing classroom time. Cool, thanks a lot.